So, hello learner, welcome to YourPedia Education. Today we are here at IIT Mandi. I am excited to take you around the lab tour of one of the rarest and prestigious and world-class laboratory in IIT Mandi, that is C4FED, Center for Design and Fabrication of Electronics Devices. So, I have got an opportunity to interact with Sumit, who is PhD scholar here. First of all, Sumit, thanks for sparing few minutes for us, right?
It's my pleasure.
So we have got to know, we come to know about this laboratory from the, basically head of this laboratory, Mr. Satinder.
Satinder Kumar Sharma.
Okay, Mr. Satinder Kumar Sharma, he told us that this is one of the rarest and unique lab we have set up here in the IIT Mandi. So see, IIT labs are very important in the academic journey of any student because they provide them an opportunity to get some real and hands-on experiences. So let's dive into the worlds of IIT lab and see what kind of cutting-edge research is going on here. So guys, for electronics people who are graduated, they might have studied in brief about basically etching, lithography, ionization, photoresistivity, these all kind of stuff. But today I'm going to show you people the entire lab tour, how this process works, what are the subsequent stages and what are the different experimental setup used in this journey. So Sumit sir, first of all, we are starting from this section, right?
Right.
So can you tell me, this lab is open for all discipline student or it is only for the electronics?
No, actually, it is like a transistor fabrication facility.
Right.
But right now, this is a multidisciplinary type of research.
Right.
So it is dedicated to electronics, but although it is open to everyone.
Right. What makes this lab unique from the other labs in other IIT?
So this is this is a class 100 clean room facility.
Okay.
So and from lithography to the from testing of a device,
okay,
and for all the processes required,
right,
some depositions, metallizations, lithography, up to we have lithography up to 5 or 10 nanometers of
right,
resolution.
Right.
So it is provided under the same roof.
Right. Since in our day-to-day activities throughout our schedule, we keep on using the electronics throughout the entire day, and we are believing that we get some more smart electronics. But what is the logic, what is the process, and what is the manufacturing, and what is basically the hard work behind that smart electronics, that we will try to learn today through Mr. Sumit, and we will see what kind of experimental setup this lab have and how they are utilized at different stages of the fabrication. So can we start please?
Yes, sure.
Okay, so first we start with this machine.
So so first of all, I welcome to you to C4FED.
Okay.
So this is a class 100 clean room facility. So you can see around here, there's a lot of instruments are there.
Right.
So we can start with the one by one.
Okay.
So this is you can see from here, this is an FESM,
okay,
that is a field emission secondary electron microscope.
Okay.
So this is a microscope. Generally, we can, if you want to see at the nanometer scale,
right,
so you cannot use a general microscope like an optical microscope.
Okay.
So for that we have to use a scanning electron microscope.
Okay.
So this is used to at very high magnification,
okay,
and very low resolution. So high resolution also.
Okay.
So to see the features at nanometer scale.
So up to what nanometer it can go? Any idea?
Yet it can see up to 5 nanometers of
So is it predefined or we can adjust it? We can scale it?
No, it is from micron level to the lower level. We have to magnify it, okay, using the controllers. Okay. We have to magnify it, and it can go up to that level.
Okay, great.
So it's a minimum we can go up to sub 10 nanometers, okay, resolution.
Great. Right. Okay.
So this is the next one. This is a optical depth profilometer. Okay. So it is from Bruker company. So it is used for optically. It is used to map our surface, and it will help to tell us what is the depth of the pattern or a specific pattern or something.
Right.
We can see this is a coin we have imaged here.
Okay.
So it is.
So this coin is imaged through this one, right?
Yes, this coin is imaged through this one.
Okay.
And it is showing, it is having a height of this. The highest one is around 136 microns.
Okay, fine, great. Okay.
Right.
So we got this one. I guess this is the silicon wafer, right?
Yeah, this is a silicon.
So mostly graduate student might have heard this name, that the wafer they
you can
keep
open
on
it
studying,
and
right?
you can see it. So yeah, so this is a silicon wafer.
Okay.
So this is a basic building block for all the electronics, and so all the features and all the patterns and the transistors, and chip will be fabricated. It will further dice. First we have to fabricate all the circuitry over here,
right?
Then we have to dice it into certain small amounts. Then we will pack it into some packages.
Great.
So then we have a finally complete chip.
Okay. So then, can we come to this?
Yes. So this is like India's one of the first instrument that is called helium ion beam lithography setup.
Okay.
So this is a lithography setup that is having the resolution of up to 1 nanometer.
Okay.
And it is used for patterning at very low scale.
Okay.
Like in sub 10 nanometers of lithography is possible through this machine.
Right,
so it is using actually the helium ions
Okay.
to pattern the
so how it's different from the other kind of the lithography technique that we have some other kind of also like electron lithography is there like
yeah. So basically like it is a much advanced technology than the electron beam lithography.
Okay.
Because it is using the ions.
Okay.
So you know, like ions have a higher mass than the electrons.
Right.
So it will go deeper into the substrate.
Okay.
So the backscattering will be avoided.
Okay.
So it can, like electron beam lithography is also claiming like it will go up to some 5 nanometers of range.
Right.
But for like due to using the ions, we can go up to like 1 or 2 nanometer also.
Like, you know, someone is coming to this lab and he want to use this experimental setup.
Right.
So what kind of module you people have? You first train them, or what is the procedure basically?
No, like we have a training programs.
Okay.
Otherwise in the whole country anybody can approach us.
Right.
Like we have a requisition form that
Okay.
is available on the online.
Okay.
And somebody can fill it.
Okay.
And availability of the slots will be given to the
You mean to say if
user.
somebody is working somewhere else
Yes,
in the same domain and
Yes.
he need the access to these kind of facilities, so he can approach IIT Mandi.
They can approach IIT Mandi. There is an online resolution form. He
Okay.
will fill it
Okay.
and give us the requirements, what
Okay.
actually he want to do.
Okay.
Like he will give us the proposed plan.
Okay.
So if the something is like we can provide, we can definitely will provide, and we will doing from last 4 or 5 years.
Right. That's great. That's good. Okay. Can we proceed that?
Yes. So this is another. This is also this is called atomic force microscope.
Okay.
That is also uses for like at a nanometer scale to see the morphology and thickness of the different materials.
Right.
Right.
Okay.
So it is like this is it sees through the electrons.
Okay.
But it sees through the like a very sharp like a tip having a resolution of like
Okay.
10 to 1 nanometer.
Okay.
It's a cantilever type of scanning.
So basically, which you will prefer, this one or this one?
No, it's based. It depends upon the the materials and type of the imaging or type of the study we have to do.
Okay.
So some materials we can do with this one, and some with this one, and some can both we can see.
Right. Now here is one question, like you are doing your PhD, right?
Right.
So you have started from the scratch, obviously. Once you have completed master, then you start doing PhD.
Right.
So when you first time join these kind of the laboratory, how difficult is for a researcher to start the journey with these all instrumentation? How to start, you know, basically learning that how to utilize them in our study? Because instrumentation in the labs are not only for the showcase.
Right.
Obviously, one is coming there, he also need to know how to use them,
Right.
how to exploit them for their own research.
Right.
So basically, your seniors or your faculty, they guide you people for this or what?
Definitely, our our mentors, our supervisors, they bring that technology to us, and they will provide the trainings, and they come and they came into the lab also, and they will teach us in the beginning,
Right.
like how to handle an instrument and how to do a certain set of experiment,
Right.
and how to do that. So
Okay.
it is we cannot do arbitrarily anything. So it is a complete step by step process.
Okay.
So we learn from our supervisor definitely, and from our seniors also.
Right.
So but like ultimately we are doing our PhD in the fabrication field.
Right.
So we have to very certain about the technology
Right.
and the processes, because it is like error rate is very less.
Right,
That in like we are fabricating at nanometer scale, so it is very we cannot tolerate even a small error in that during the measurement or some pattern deposition or any step in the fabrication process.
Right. See, every lab is having its own requirements. Since
Right.
you are doing PhD under this lab or with this lab, you are associated with this lab, right?
Right.
As per your experiences, what are the 2 to 3 requirements person should have if you want to adjust in these kind of the lab, basically into the domain of device fabrication, design and manufacturing?
Yeah, that is one is the what I believe personally I believe one is the criteria to come into the IIT. That is the first stage,
Right.
like having a GATE score and all these things.
Right.
Then after that you have to love to work with the machines, and you have the curiosity to work on these high-end instruments,
Right.
because these instruments are this is we are meeting with the world level.
Right.
So even the highest universities in the world, they are also using the same
Ultimately,
technology.
conclusion is that whatever you will show to the world, that
Yes.
will be through these instrumentation, right?
Yeah, through
They are your companion in the
Yes.
journey, right?
Right.
So can we move ahead?
Yes.
Okay, so these are also the chips of that wafer, right? Small chips of that wafer, right?
Yeah, that what I saw you earlier, that is a complete wafer that
Okay.
then we dice into some smaller sizes,
Okay.
and then that will be used for like some imaging for this atomic force microscope.
Right. Can we go for the next one?
Right. So this is a lab 2.
Okay. So this is again the lithography lab, right?
Yes, this is again a lithography lab.
Okay.
So this is also class 100 clean room facility.
Okay.
So here we can see this is a electron beam lithography setup.
Okay.
So it is also uses the electrons
Okay.
for patterning, like patterning for I will tell you in like brief. So what we have like a pattern.
Right.
So we have to transfer this pattern into the wafer,
Wafer.
because ultimately a MOSFET circuit or anything, whatever our circuitry on the chip.
So we can't do that through masking also.
That we can do through the masking also,
Okay.
but generally we use 365 nanometer of wavelength of light
Okay.
for like photolithography.
Okay.
But here we cannot go beyond like 0.5 micron.
Okay.
Okay, but here we can go up to like sub 10 nanometers also.
Okay. Fine. So
Okay.
those systems
So
are
they have the very high resolution as compared to the optical lithography.
okay. Great.
So that is the uniqueness of those systems.
Okay.
So like if you want to pattern sub 100 nanometers of patterns, so we are using that the electron beam or either helium ion.
Okay. So you can show me some demonstration, basically how this part happen.
So this is just like this is a demonstration. Like this is a SEM is attached to that one.
Okay.
The scanning electron microscope is attached to that one.
Right.
So these are some images.
Okay.
These are the transistors. Actually, this is a FinFET.
Okay.
So like this is a drain source and this is a gate pattern.
Okay.
So like we can see through other images also. This is drain and source.
Okay.
Those devices we have fabricated here.
Okay. Right.
Okay, and so this is a magnified image
Okay.
of the drain source and gate. So like you can see the scale.
Okay.
It is around 100 nanometer, 300 nanometer of the
Right.
gate length.
Right.
So this is the drain source and gates.
Now this pattern you will use, right?
Yeah, these are this is the image of the final device.
Okay.
This is a already fabricated device. So
Okay.
you can see this is a FinFET. So this is a drain source. These are fins.
Right.
These fins having the like thickness of like 20 nanometers,
Oh.
15 nanometers,
Right. Right.
and this is a gate. This is a gate.
Right.
So once we have device, like when we fabricating, it is a process of we are using like 5 to 10 masks or 20 masks
Right.
for the completion of the one device.
Right. Right.
So at each stage we have to do the patterning, do some metallizations, some etching, and we have to analyze in the SEM. So it is done properly or not. Some short is not there. Some metal will remain there or not.
Sumit, now we are done here with the pattern, right? Now
Right.
what will be next stage after this?
So after that, like this is lithography.
Right. Right.
So there are certain things also there,
Right.
like deposition of metals,
Okay.
deposition of like dielectrics.
Right. Right.
That we will do in the other labs.
Okay.
So through the sputtering technique, E-beam evaporation, and the atomic layer deposition.
Right. Right. Right.
So that is in the next lab.
Okay. Okay. So what is the use of this?
So this is a fume hood.
Okay.
So this is a fume hood. This is having a laminar flow.
Okay.
So this is used for like preparation of the sample.
Okay. Right. Right. Right.
Okay, so in the complete process, we have to use it for preparation, like applying the photoresist, removal of the photoresist.
Right.
So it is it's a sub-controlled environment.
Right. Right.
Although this lab is also controlled, but it's a sub-controlled environment.
Okay.
So we have access to different gases, water, DI water.
Right, right.
So that is having all the things here, and it's having the laminar flow. So like the contamination will not go to the sample.
True, true. And this is photolithography, right?
Yeah, yeah.
Okay. Okay.
So this is a photolithography.
So can you show us the mask for this?
Yes, definitely. So this is a mask.
Okay.
Like this is one of the masks.
Okay,
So
might
it-
be these two terms student might relate with because they study these term on very basic term photolithography and masking.
Yes.
So this is basically mask used
So
for
you
the
can see
photolithography.
here it's having like if you zoom it here, so it's having a this is a some transparent part
Right, right, right.
and some opaque part.
Right, right,
The
right.
opaque part is basically a chromium metal,
Okay.
and other is a transparent one.
Okay.
So this is having a feature of 1 micron.
Oh. Great.
Okay, if you imagine what is the 1 micron, like our human hair is average like 50 to 100 micron thick.
True, true.
Like typically you can say like 70 micron thick.
Right, right.
So it is like 1 micron,
Right, right.
the 1/70th part of the our human hair here.
True, true.
So that we can do with the like we can do up to like 1 nanometer. Sorry, 1 micron.
Micron.
Sorry, 1 micron with this machine.
Okay.
But if you move above than that, like much below than that, so we have to use the electron beam.
Okay. Great.
So this is also another machine.
Okay.
So this uses a physical mask.
Okay.
This is uses a like it's called a maskless.
So it is also photolithography.
This is also photolithography. This is also using 365 nanometer wavelength. This is also using 365.
So basically, what is the substitution for mask here?
So here is like we can make a CAD mask.
Okay, CAD mask.
We can make a CAD
Then you
mask.
will have some file and these all.
Yeah, we have a file, like we have a GDS file, we can import it into the software,
Right, right, right.
and it will follow the software one.
Okay, okay.
Similar to the electron beam,
Okay.
but here it is like the source is different. Is the electrons are source, here is the source is the light,
Okay.
365 nanometer. So this is a stepper.
Okay.
This is a stepper that is used to like see what is the step height
Okay.
of any pattern we are making,
Okay.
like any metal
We are depositing.
thickness. So it is a stepper basically.
Okay.
So it will give us the measurement what is the thickness of the particular deposited layer.
Right, right, right.
Abhi next
Okay. So now, Sumit, can you tell me what is that?
basically this is a pass box,
Okay.
and it is used to like whatever the things coming from the outside to the clean room,
Okay.
it will must pass through this box.
Okay.
Okay, so because it is having some controlled environment,
Okay.
it having a UV sterilization,
Okay.
then it having a like air circulation.
Okay.
So first we keep the material inside that one,
Okay.
then we will take it inside,
Okay.
because that whatever comes from outside may have some contamination.
Right.
So
So
we
that's
have,
why we take the shower in the beginning, right?
yes, that's why we take the shower in the beginning.
Okay.
So this is the like we have to like whatever, because ultimately the source is coming from the outside.
Right, right,
Even the human beings or even the any
Every
item.
raw material is coming from the outside,
Yes,
right?
because this is a 24/7, it is running
Right, right.
and it is maintaining its class.
Okay. Right, right.
So
Basically, what is this entire setup about?
so once we fabricated our device,
Right.
so we have to test it electrically.
It's parameter testing.
Yes, it's a parameter testing.
Okay.
Like if we take example of a MOSFET,
Right.
so we have to test it's the drain current. What is the drain current? What is the threshold voltage?
Okay.
Okay, so it is behaving like as per the expectations or not.
Okay.
So we have to test it.
Okay.
So it is a parameter analyzer.
Okay.
So it's a Kitle. It's a very sensitive instrument.
Okay.
It can measure the current up to like femtoamperes.
Femtoampere.
Yeah.
Okay.
So it is it's a MOSFET circuit.
Okay.
So here we can control the parameters like applying voltage, applying current through this software.
Okay.
And this is
So this is entire simulation, right?
no, it is not a simulation.
Okay.
It is an actual device parameter, analyzing the parameters and
Okay.
measurement of the parameters of the MOSFET.
Right.
Actually,
Right, right.
not a simulation.
Okay.
Here, what I mean to say through the software, we can fix the voltage range.
Okay.
At what range it will be measured.
Okay.
That particular instrument or device under test, at what range it will be measured. So it is a probe station.
Okay.
So it is having the gold chuck, and these are called micro manipulators.
Okay.
So these are the probes,
Okay.
and these probes having having a apex of like around 30 microns.
Okay.
So we have to make up our pads on our devices. So we will probe it, and once we probe it, so we will measure through that software,
Right, right, right.
and we'll run the program. So it will measure those, record our current voltage
Entire parameter.
values.
Okay, okay, fine.
Yes.
Okay.
So this is a clean bench.
Okay.
So this is a spin coater.
Okay.
And this is used for spinning the photoresist around the wafer.
Right. Right.
And once the photoresist is spin coated through this instrument, then we bake it on the hot plate.
Okay.
And after the hot plate, we can use the lithography.
So what material you are using for this specifically?
This is like photoresist. The photoresist are like a light sensitive material.
Right, right, right.
So it's having the property, it will change its like properties when exposed to the light.
Right, right.
Or the like electron beam. There are
Okay.
different kinds of photoresist.
Right.
Some are like photosensitive, some are electron beam sensitive.
Right. So how you decide that this material is having better sensitivity or this is having lesser? You already have decided on the basis of that you select or what?
No, that is available in the market, and like it is like our part. We are doing like it is a job of a researcher.
Right.
To distinguish what material, what application, which material will be used,
Right, right, right.
or what resolution he wants.
Right, right, right.
So on decided upon that, we will choose which photoresist we will use.
Great, great, great.
So like generally two types of photoresists are there. One is a positive photoresist, one is a negative photoresist.
Okay.
And so that are available. So one of the uniqueness, like in our lab, we have indigenous photoresists also.
Okay.
Okay.
So it's by some other department or you electronics department is working on this?
Yeah. So in the from the IIT Mandi itself.
Okay.
So we have like our guide also have a group.
Okay.
So he is also working the photoresist. Okay. Like other Professor Subarto is also working. They are working collaboratively, and they synthesize the resist in house. Okay. And we test it through those machines. Okay. That I already tell you, like electron beam, helium ion.
Right, right, right.
And they test it, and further they will send it to some other labs also for verification. Okay. Like for like EUVL, like that will use in the industry to like, because this is a slow process. This cannot be used to fabricate a chip. Right. Because chip contains millions of transistors. So if you go to for patterning for million devices, billion devices, so it will take time. Right. So that will be done through the EUVL. So we will send those samples to other countries like US. Okay. They will check the properties of the resist. It is working at their resolution. Like in currently that sub 10 nanometer is required. So
in this entire process of design and fabrication, from the basic raw state to final stage of the prototyping, right, do you people need to access other labs also, or this is enough?
No, for prototype this lab is enough. Okay. But for making it, like what I am saying, like we send the samples, that is like our checking the photoresist, our indigenous photoresist. Right. That is like for the like industrial application. Right. Because we know that are working on for our electron beam, our helium ion. Right. But ultimately in the like mass production, the EUVL we have to use. Right. So for checking that EUVL is working for that, but for that resist is not, that we have to test with the EUVL itself. Right. So we send to the devices or our samples to the EUVL screening. Great. Right. Okay. So this is a next instrument. Okay. So this is called like glove box. Okay. So this is for specific some material that we cannot expose to the air. Okay. Like it is that materials have to be synthesized in the control environment. Okay. In the presence of argon. Right. Not in atmosphere. Okay. So this is for like some faculty, Dr. Ranveer is working on that one. Okay. So he is fabricating the solar cells. Right. Perovskite based solar cells. Okay. So he is using that one. So because it is required, so we cannot expose it. We make a whole device inside this one. Okay. Once it will be done, then we will take it out for the characterization. True. Okay.
So can we go ahead?
Yes.
Okay, so finally this lab is all about what?
This this is lab 4. Okay. And this is a class 1000 lab. Okay. So this you can see in my left hand side, this is a sputtering cluster tool. Right. So this is having a like we can deposit like we are making a.
So basically this is an entire deposition setup.
Yeah, this is a deposition setup. Okay. So like for example, we can take like we are fabricating what, like a MOSFET, for example. So for like semiconductor, I saw you the like the wafer
was there.
That is a like the channel material. Right. is silicon
Raw
wafer.
material for that.
Yeah. Upon that we have to deposit the insulator layer.
Right.
Like we can see the structure.
Silicon
MO,
dioxide or something it can.
Yes, metal oxide semiconductor.
Right. Right.
Then another step is we have to deposit a insulator.
Right.
So we have a a set of a range of deposition targets.
Okay.
So we can fix those deposition targets into that machine.
Okay.
And we can do the sputtering of that particular material.
Okay, great. So it means that whatever MOSFET structure we see, that as you told, MOS, metal oxide, and then we have the semiconductor. So
Right.
that deposition is basically through this entire setup, right?
Yes. So we have a RF sputtering and
Okay.
as well as the DC sputtering also.
Okay.
So we can deposit the metals also with this one.
Okay.
Okay, and we can use for the oxide deposition.
Right.
Also.
Right. Okay.
And this is like a PECVD chamber.
Okay.
Like plasma enhanced CVD chamber.
Okay.
And this is designed by our supervisor itself.
Okay.
So we can use this for multi-purpose. We can use for the annealing also, like some oxygen plasma also,
Okay.
and for other purposes also.
Okay.
We get like a custom-made tool.
Right,
we can use for various applications.
Okay.
And this is a thermal evaporator.
Okay.
So some metals we can having a low melting point, we can use with the thermal evaporation also. So this is used for metal deposition.
Okay, for conditioning of the metal you are using this, right?
No, like in any process we have to deposit the metal, like very thin metal, like 20 nanometer to 100 nanometer. So it depends upon the fabrication flow. So this is another tool, alternative to the sputtering.
Okay.
So it is using the E-beam, like principle is like it is evaporating the material in the very low pressure.
Okay.
Okay, and this is a sputtering. Sputtering is a physical knocking out the material from that one.
Right.
It is like a IR based, heating based.
Okay.
So we melt it, then it get evaporated.
Okay.
Under the very low vacuum.
Right.
It is like it's knocking out.
Right. So ultimately what I have observed that in this entire setup there are multiple experimental setup to do the same activity.
Yeah.
Right. So it depends upon the kind of adaptability you
Yes. What type of novel work we are doing.
Right.
So upon that we have to. It's not that then the process flow is designed according to that one.
Right.
Okay, what are the processes, what materials they require.
Right.
But suppose I am doing my research on the germanium FinFETs.
Right.
Okay, so my process will be different and someone else process will be different.
Right.
Okay, some machines are the same, but like our material requirement, material selection is different for me, and other person having the material selection is different. Different. So, but they have to design it, then they will come to us. Right. Then they do the experiments and they will implement that particular process flow. Finally, he will able to fabricate his device.
Okay, so this is the entire setup of this lab, right?
Yes.
So any segment we have left? Please?
Yeah, these are some. This is our reactive ion etching tool.
Okay.
So basically, we talk about the deposition here. So this is a tool that is reactively like a plasma-based etching. So it will remove the material.
Okay.
Like for simply, I'm saying it is removing the material from the like unwanted material. We do the same thing. We pattern. Okay. And we have exposed and unexposed parts. So where we want to remove it, we have some trenches there in the resist as a hard mask, and we can remove that material from that one.
So that is the entire setup for this.
Yeah.
Okay, great.
So this is it is using some selectively using some specific gases for that one. Okay. So it will selectively to some material and not selected to other material. Right. Means some gas is selective, like it will etch one part, not affecting the others.
True.
So that is a reactive ion etching. Great. This is another tool that is called ALD, atomic layer deposition. Okay. So it's also a deposition tool, but it is having it will deposit a layer by layer, one atomic layer in a one cycle.
So what is that resolution of that layer?
It is typically one angstrom of layer, one atomic layer. Okay. In a one cycle. Right. Like if you want to deposit a thicker one, so we have to run those cycles in a continuous fashion. Okay, great. Like that is a program controlled. Okay. So we have to give the precursor for particular material to be deposited and the number of cycles. So it will deposit that one. Okay. So this is another parameter analyzer.
Okay.
So that I already shown you.
Yeah,
So
that was one there, right?
that was one there, but that is having a control environment.
Okay.
So it will test our like a device from minus 50 degrees Celsius to up to 300 degrees Celsius.
Okay, great.
Okay, like because we have to test our reliability of our device and circuit.
How it will operate under different conditions?
Different conditions. So we'll providing the different temperature range.
Right.
And these are some additional SMUs.
Okay.
So although we are working on very low technology nodes,
okay,
low power technology nodes,
okay,
but some devices, some students, some researchers are working on a very high electric fields also.
Okay.
High power devices,
right.
like gallium oxide.
True.
Like those are used in some sensors and in engines.
Right.
Like having like high power devices. So these are the SMUs that can provide the voltage range up to 2 kV.
Oh.
So this is. So आप पूछिए, रोकिए.
So Sumit, we have done a lot of discussion regarding the experimental setup. So when you're working in the lab, obviously various instruments are working parallelly, right? And there might be hazardous condition which might be very difficult for a person to survive in the long run, right? So how you people are putting your safety precaution for those situations?
Right. Fortunately, until now there is no such incidents.
Okay.
But before coming to the clean room, the student must have to pass some the literature will be given to him.
Okay.
And some classes will be taken by the senior scholars.
Right.
And after that he have to pass some test.
Right.
To how to work in the clean room.
Okay.
So after that he will, until unless he is not passing that exam.
Okay.
And not go through the safety measures.
Okay.
We will not allow to have access of the clean room.
Okay. Great.
Okay. So, but for the safety of the student and other things, this is a fully automated lab.
Okay.
So you can see that these are smoke detectors.
Okay.
These are some
sensors.
These are some sensors, some gas detectors.
Right.
You can see there also. These are the gas detectors.
Okay.
And we have to it will sense that if some leakage is there, some gas is there, so these detectors will sense it.
Okay.
And it will trigger the alarm.
Right.
And this we have a nitrogen suppression, like fire extinguisher nitrogen suppression setup is also there.
Right.
If something goes wrong, so it will it will turn it on automatically. Okay. And it will distinguish that particular
so
alarm.
There is no point of worrying, right?
No, not point of worrying. And then we have some emergency exits also. Right. In the clean room.
Right.
That is trained, that the person who is working here, that is already known those things in advance. Right. So if some situation is there, what has to follow. Right. When we come inside, we have a very long standard protocol. Right. Like wearing hat and this, having a shower. Right. But in the emergency, there is a certain other things. Right. So we do not need to follow that particular steps. Okay. We have to first save our life. Right. True. Okay. Can we go to the next slide? Yes. Okay. So now, what is this entire setup here? So this is a lab 5.1. Okay. So it's basically this is a high temperature lab. Okay. So you can see here, this is a 3D printer. Okay. So various students from different departments, they can access it. Okay. And they are making some molds, some geometry. Right. Using a 3D printing. Right. And you can see here, this is the electrospinning setup. Okay. And we can deposit the from a solution that is in the liquid form. Right. And we can deposit in a form of fibers. Okay. Nanofibers. Right. So it is a collector, and that liquid will be filled in the syringe. Okay. And this is controlled through the software. Okay. And it will make out fibers. Okay. So that fibers can be used for different applications, like sensing applications. Right. E-nose. Right. Like those various applications that we can utilize for. Right. That one. You can see this is a 3-zone furnace. Okay. That can be used for oxidation, and we can do we have a custom CVD also attached to it. Okay. So we can use it for chemical vapor deposition also. Okay. And these are the hot ovens. Okay, so these are the sample. These are the sample boxes. Okay. This is called desiccators. Okay. Once the researcher is making those devices, okay, and in between he will store those samples
Okay.
in those boxes.
Right.
So it will not expose to the air, because
Right.
most of the materials, they are reactive with the like oxygen,
Right,
and
right.
so we have to be protected.
Right. So this is entire about this lab, or we
Yes.
are left with some other segment also?
No, only this is covered.
Okay.
Only that like to maintain that particular environment.
Okay.
Because here is that particle count is maintained, humidity is maintained,
Okay.
pressure is maintained,
Right.
and class is maintained.
Okay.
So that has to be maintained by some equipments that
Okay.
is outside that one.
Okay.
What are the like AHU, air handling unit is there. So how they can like maintaining the temperature, humidity,
Controlling and monitoring unit is outside, right?
that outside, that is separate unit.
Okay, fine. So Sumit, the entire setup was quite impressive. So it's not an easy process. I got to learn this, that fabrication and design is not an easy process. And in coming time, if you people have interest, you want to study design and fabrication of the electronics device. So IIT Mandi is the new generation IIT, which is well equipped with the entire facilities which one need to become a good researcher on the experimental level, as we have tried our best to cover the entire experimental setup in this video. So for more information, you can visit their website and explore more about this laboratory. Thank you, Sumit.
Thank you so much.